So in this lesson, we'll look at what is simulation, what are different types of simulation for casting. Okay, and within that, we'll focus on the first one, which is the easiest to develop, easiest to implement, and a little more reliable, which is solidification simulation. So we'll discuss what is solidification simulation, what are the critical inputs which ensure that your results are more reliable. Okay? And then we will also introduce one method at the end which helps you to optimize the design automatically or semi-automatically. It also helps you to interpret the results of simulation a little more reliably. So that GVM, gradient vector method, will introduce at the end of this lesson. Okay, so quickly, what is simulation? It is nothing but a mathematical model of a real life phenomenon. You make some assumptions, make some approximations, otherwise it's impossible to mimic real life. It's an approximation or simulation of that. But at the end of the day, you have to implement that mathematical model in a computer program. So you are actually able to give inputs and say what is going to happen for this set of conditions or cases. So at the end of the day, the job of simulation is to predict what is going to happen. Number one. Number two, sometimes to analyze what has already happened and see why it has happened and what I should have done to prevent that, or what I can do in future to prevent that. So there are two applications of simulation: is to predict or prevent. Okay. Now, real life to simulation, a quick comparison. If you can always, instead of simulation, do an actual experiment on the shop floor. You want to find out what is going to happen if I increase the feeder size and reduce the point temperature and may put the gate here. You can always do the tooling and actually figure out on the shop floor. That's real life. Okay? And real life is always truth. Simulation is only approximation of the truth. Okay? But the real life experiment can be expensive, it can take more time, it could be dangerous, it may not be safe, or it may lose some productivity. All the disadvantages are there. Also, you cannot always extrapolate and interpolate too much. In simulation, there is no limit of size or shape or what you can do with that. And it's usually much faster than the real life experiments. So just a quick example here. So if you look at this part, okay, and then you have a real shop floor experiment done, and then you find there is a porosity there, but really don't know what could have caused the porosity or shrinkage porosity. Okay, so you could have saved production resources by actually doing it by simulation. Okay, suppose you want to develop a new casting without trials on shop floor, can you do that? Yes, we can do simulation and maybe do just one trial run on the shop floor to verify the simulation is right. Okay, you can improve your yield, reduce your cost. But another big advantage coming up is when designers and foundrymen discuss an issue or a problem, usually they blame each other. Foundries may say, no, your design was not foundry compatible. And designers may say, no, but I got this casting from Brazil and they are able to do, why you are not able to do it? Okay, but for all they use a different material or different equipment or different process. Okay, so this helps in discussions, a little more friendly dialogues and a little more scientific discussion, a rational way of arguing instead of saying I know better and think kind of discussion arguments. So what takes, let us say, one working week on a shop floor in a real experiment, you can do it perhaps in 1 or 2 days maximum with a simulation. So you do save directly time, at least 50% time, if not more than that, and not to forget the production stoppage and material and energy and labor and everything else. So this is definitely better than in experiments. Also, you sometimes get better insight in simulation than in shop floor. Shop floor, you do not know what to see where. Simulation is all transparent. You can see everywhere. Okay. Now, some of the points coming up saying what really affects the simulation. To start with, the mathematical model itself which you have used starts affecting. Is the model right? Are the equations complete? Are the coefficients complete? If they are not, then obviously your starting point itself is wrong. Then you come is, you are going to divide the part into a large number of small pieces, what's called as elements, mesh elements, or you can say voxels, what different languages are there. Now when you subdivide a large casting into small parts, depending on what is the shape of the voxel, is it a cubical, rectangular or pyramidal or whatever, the approximations are different. So if you want to have cubical elements only, you must have a large number of elements to get high accuracy. So how are you dividing is a question. Then one critical input is the heat transfer coefficients. No one really knows, yesterday we discussed that. What is really the heat transfer coefficient from metal to mold, mold to air? Okay. Are there any models for that? How do you know the air gap thickness which affects your heat transfer coefficient? No one knows that. So it makes an approximations there. Okay. And finally, okay, you have the pictures on your screen. Okay, there is somewhere red, somewhere yellow, and somewhere green and white. How do we know how to interpret the results? Because interpretation, like X-ray of a doctor, X-ray by a doctor, if you interpret wrongly, you are putting a wrong solution in place. So that is also equally important, apart from all these four things. So these affect your finally accuracy of implementation. So when you divide the component into the elements, what starts off is it a structured mesh or an unstructured mesh? Structured essentially means it's all, you can say, a fixed grid or a uniform grid. Unstructured means you can put a smaller element where you need higher accuracy, a little bigger element like in outside mold walls where you don't really need high accuracy or heat transfer is not much. By doing this small element in critical area and big element in outer areas, we can reduce the computation time. But what people forget is that the mesh generation itself can give you a lot of headache. Creating a structured mesh is automatic and fast. Creating an unstructured mesh is highly interactive, can take a lot of time, can introduce a lot of errors also in the process. So you have to be careful about the gain and loss from structured and unstructured meshes. Okay. Now simulation process itself is a basic flow chart. You don't really need to know the black box. Simulation like a black box. We give some inputs, you see some outputs. But this is a quick view, a very simplified view of what is inside the black box. Okay. First, the black box contains the fundamental equations for your mass balance and energy balance and momentum balance and so on. Those equations, number one. Number two, they convert those equations into a system of partial differential equations which are solved after you discretize. When I say discretize, you divide the space and divide the time, both into smaller steps. And you solve those system of partial differential equations. Now you can divide the time in different ways and compute it in either explicit or implicit or a mixed kind of method.
Excuse me, sir.
So this is FDM is finite difference method, FEM is finite volume method, FEM is finite element method. In a way, what I showed you earlier, the structured mesh typically is FDM, the unstructured mesh is typically FEM as a starting point. Then you have, we solve the equations in some computation method. Okay? And finally, you get the solution in terms of what you get at the end of simulation is temperature at a location XYZ at a particular time instant tau. And that information you can process further to find out where is the hot spot, how is it feeding, how is it filling, and so on and so forth. Okay. This is energy equation. I will not even describe it in detail. Okay, you can see it. And then you have another very critical thing is the flux, heat flux between the interfaces. We can even talk about solid to liquid interface. Liquid to solid interface within the metal. Then solid metal to the mold across the air gap, and from within the mold, and then from mold to the air. The interfaces between any two different kind of materials or bodies, the interfacial heat flux equation has to be defined properly. And here is where a lot of approximations and coefficients come into picture. So let's just quickly review. What are the inputs which really make a difference to the simulation? Number one, I must have the correct part geometry. You can't have machined part for simulation, you must have an as-cast part for simulation with all the allowances and drafts. But very critically, if there's a drill hole, you must remove drill hole. That's what creates maximum error in a simulation. Then you must have the properties of the both part metal as well as the mold materials. When I say mold materials, you're talking about mold and core and chills and all those other things, okay? Even coatings. Okay? And remember, many of these material properties are not constant but vary with time. Like density we have seen varies with time. And so with conductivity and specific heat and everything else varies with time. Varies with temperature. Then boundary conditions we just mentioned, heat transfer coefficients, okay? And especially feed aids, chill, insulation, exothermic. What is heat transfer coefficient? Does anyone have the values of that? We need to sometimes do experiments to find out the values of that. And then type of mesh, we discussed that. Then finally, before interpretation, the metallurgical models which tell you, okay, here is where shrinkage will come, here is where maybe a lap will come, here is maybe gas porosity might come, things like that. So metallurgical models to predict the actual location of defects based upon the results of temperature and gradients and so on and so forth. These are the various things which need to be there in a good simulation package. The first stumbling block itself is a material database. What people don't realize is material database, the material properties can change drastically. As you can see, percentage difference in just conductivity. Look at the difference. It's almost half. Okay, density changes by 10-15%, right? So with enthalpy, fraction solid and all that, you need those graphs or table of values at different temperatures for the composition of material which you are making in the mold which you are making. And these values are not available. Okay, they are maybe available for certain materials, common mold materials, but not necessarily for all the things. So the moment you have a new composition or a new sand supplier, you have to redo the experiments and find the values of that. People don't realize that this is one major starting bottleneck, because if you don't have properties, the FEM computations can't even start. Okay? But even bigger stumbling block, and I think I can tell you one story here that about maybe 7-8 years back, 3 or 4 students went to Fiat Research Center in Terry, and there they asked us to research on what are the most critical inputs which, if you give even slightly wrong to simulation, you can get very different results. Okay, in a way, I'm answering many of your questions. Right? So they looked at many parameters, and this came out to be the biggest villain. Okay? You can say villain because if you don't handle it right, you are in deep trouble. The villain is the heat transfer coefficient from the liquid metal to the mold across the air gap. Remember, air gap is 0 in the beginning, and then the metal, as it solidifies, moves away from the mold wall, a slight small air gap. Air gap slowly grows with time. And remember, air gap is like insulation, so the heat transfer coefficient comes down drastically. Unfortunately, air gap is not even constant for a given situation. On the top of the mold, air gap is more, you have a lower coefficient. Bottom of the mold, it's in better contact with the mold because of the weight it comes down, you have less air gap and higher heat transfer coefficient. So air gap is not constant by geometry, not constant by time, not constant by temperature, and I'm not even talking about material combinations. So air gap is one animal which no one has been able to control until now. When I say air gap and depending on it, the heat transfer coefficient. So IHTC, interfacial heat transfer coefficient, is the biggest villain in any simulation program. Okay, and so people are trying to do this in different ways. They are talking about numerical models, a table of values from experiments, okay, or reverse calculating the value of IHTC for a given case. But then that's a chicken and egg problem. You need IHTC to simulate, but then you need to simulate to find IHTC value. So how will you do? And you also always want to predict for a new case, but every new case will have a new IHTC value. So how are you going to solve this problem? That's the first or second biggest problem in simulation. So we did some experiments on this also. So we took a popular high-end simulation package available in a research lab in India. So we went there and we did 2 things. First thing we did is we actually made a real casting. So the black line here in the middle, okay, you can see this black line in the middle, this black line, that is a result from a thermocouple in the mold. So that is the truth. The black line is the truth because we measured it from a thermocouple in the mold. All other lines are the results of simulation by giving different IHTC values. Okay, and so if you look at the variation values, okay, from 100 to 2000. But if you see at some point, maybe it's about between 500 and 700, 800, the 2 curves are reasonably matching. And remember, this is an average IHTC value. It's not even time dependent or temperature dependent value. So we are able to match. So you have to do experiments like this to match the IHTC value for a particular combination of part metal, mold material, and part geometry. Okay, so again, repeat once again. These are some of the critical inputs, but if you start seeing now, the IHTC between different pairs of materials is the most critical input here. Okay, so how the part geometry is divided or discretized in different methods. Again, we are now answering your question in a sense. So if it's finite difference, it is usually cubical mesh, we do like that. In finite volume, which is good also for flow simulation, and we'll come back to this a little later. And FEM, where you can have a pyramidal or tetrahedron kind of divisions, okay, which can be used for stresses also very nicely. So FEM is good for solidification as well as flow as well as stresses, whereas FDM or a finite volume is good mainly for solidification and flow. Okay, so how it is solved, I just mentioned to you passing, it can be solved by explicit or implicit or a mixed method. I will not go more deeper than that at this point. But let's look at this slide carefully. You see the 2 black lines representing the liquid and the solid. It's like, in a sense, the it's like onion shells, the solidification is moving. Okay. In this case, you can see the outer one is solid, inner one is liquid, so it is moving from outer to inside. The green line here represents the direction of heat flow. Heat is flowing from liquid to solid towards the mold boundary. The blue line is showing you how the solid liquid boundary is moving from outside to inside. And the red line here is showing you how the inside is feeding the outside. All of these are parallel to each other. Okay? The direction of movement, direction of heat flow, direction of front, liquid solid front, and the feeding direction, all of them are parallel to each other. And the last one, the red lines are of most interesting or most interest to us, because these are lines which represent how the feed metal flows and where I am going to get shrinkage porosity, or am I getting my controlled progressive direction solidification or not. Okay, so we'll look at that in a little more detail. So how do we capture that feed path? So there is a method called as gradient vector method. Okay, it's compared to FEM or FDM and all numerical method, this is far more recent. FEM was invented, if anyone can guess when FEM was invented? How many years back? Anyone? Academics? World War II. That's right. Okay. In fact, computers and FEA was invented almost within about a few years of each other. Okay. So FEA is as old as computers. Alright. Unlike that, the GVM is hardly 10 years old, 10, 15 years old. This is far more recent technique for computing feed paths. If you notice, are along the direction of the liquid front, but the liquid front essentially, liquid solid front essentially is nothing but an isothermal contour. The entire front which is freezing has to be at the same temperature. So the feed paths are nothing but perpendiculars to that. And you can see it in this slide. Those orange and yellow and the brown lines represent equal temperatures, so they are all freezing at the same time. So where do you see the maximum temperature gradient? Maximum temperature difference perpendicular to that. Along the line temperature is same, perpendicular to the line you have the maximum temperature difference. And that becomes your preferred direction of feed metal flow. First you understood the isothermal lines. The lines which you see, curved lines, and we asked you to draw the lines for a similar shape. Okay? Those lines represent equal temperature because they are all freezing at the same time. And of course, the outer layers all freeze at the first time, then the inner layer freezes after that, and so on. Okay? So along the line, temperature is same. So if I say, where do I see if I given any point, suppose you take a point on a particular line, and I say around me, in which direction I am likely to find the maximum temperature difference, it is going to be perpendicular to the line. So along the line it is same. Perpendicular you have the maximum chance of finding the maximum difference.
What are the red lines there?
The red lines are there, exactly. So red lines represent the preferred direction of feed metal flow, which are nothing but my maximum temperature gradient lines. Okay? So that is what I am trying to find out. So what you can say is feed path is nothing but the trace or the path of the maximum temperature gradient, and a hot spot, if you see in this picture, is nothing but the convergence of the feed paths. Don't worry about direction of feed paths here. Feeding is from inside to outside, but you can say directional solidification is from outside to inside. So feed path is actually the reverse of the arrows here what you see. So the feed paths eventually converge, and where they converge is a hot spot. That spot is feeding the rest of the casting, and that is going to have a shrinkage defect. It's a beautiful way to find the location of shrinkage defect and look at directional solidification without computing temperatures everywhere. If you can somehow find these lines directly, three-dimensional lines directly, you save a lot of computation time. That's a big technological development over FEM. So how can I calculate that? There's a nice method without going too much into mathematics here, just a little math. The first equation nothing but your high school conduction equation written in a different way. If you notice this, you know Q is equal to Ka dt by dx, or S is distance here. So if I put dt by ds on one side, which is your, in a way, gradient. G is your gradient in a particular direction. Gradient is dt by dx. Here it is dt by ds. Same equation, minus 1 by k multiplied by Q by A. Q is heat, A is heat transfer area. And Q by A in a way is your flux. Heat flux is heat per unit area. How do you get Q? What is Q here? The amount of heat transferred given up by the metal. What is that? Specific heat into temperature fall plus latent heat. That is what you see in this equation. What was discovered, and the big landmark discovery here was, you find the net gradient or the resultant gradient in a particular direction is nothing but the vector sum of individual gradients around a particular point. So if you see that small triangle there, the blue triangle, you see the small gi. Gi is a gradient in a particular direction, and gi equation already is given to you. But the individual gi's around the point, if you take a vector sum, that is what you see in the black lines. The vector sum is finally from the starting point to ending point. That is a red line. The red line represents the net gradient at that point, which is perpendicular to the temperature contour. So without finding temperature contour, you can now find a gradient, which is a beautiful mathematical technique here. Okay. So, and then how to calculate GI for a 2D and 3D? You can approximate. You can say for a 2D it is nothing but the beta is the angle of that segment or sector. Pi is 180 degrees multiplied by your heat content volume by heat transfer area. Essentially like modulus, you can say. In fact, in the beginning we used to call it as modulus vector. But then we are able to relate it with heat flux. So now from physics we are able to say that it is nothing but heat flux vectors around the point. In 3 dimensions it becomes volume by area. And the angle now it is a solid angle. Okay. Now I'll show you how we can use that to handle other mold effects. Finally, end of the day, a simple shape is not enough. We need to talk about if there is a feeder, what happens, insulating sleeve, what happens, a chill or a core or a re-entrant corner, what happens. Now it's very easy to do all these things by going back to our original description of MEF. What is MEF? Modulus extension factor. I can introduce a factor called as your extension factor, and that I can relate saying that it is nothing but, the extension factor is nothing but the density into specific heat of the particular body in which I am interested in, divided by density and specific heat of the mold material. Essentially it means compared to mold material, my heat capacity is less or more. Okay? And in this equation, if you plug the values of chill or insulation, beautifully you will get MEF value for insulation as 1.4 and exothermic as 1.7, which matches with the manufacturer's values of MEF. So using a traditional practical notion of MEF, we are able to put it back into physics and say here is how I can take care of the effect of all kinds of mold situations and the foundry man's tricks. Okay? That is theory, right? So insulation is 0.7 because it's 1 by, in a sense it is 1 by. So if you see 1 by 1.4 is 0.7. Similarly, chill, if we said chill effect is up to a distance of whatever 3 times, right? And chill effect is typically 0.33 here. So MEF is reverse of that. So here are the first few results which you have already seen yesterday. So you can find out the hot spot, you can find out temperature, but what is really interesting to me as a researcher and a practical foundry man is the feed paths. I can actually visualize in 3-dimensional view how the feed paths are coming from different parts, how are they converging, are they meeting or not meeting, are they meeting in the feeder or are they meeting in the casting. This is a beautiful visualization, and I don't need anything else in a foundry to understand how a casting solidification takes place. And this is a very versatile method. With feed paths, we can look at many defects in the foundry. I will show you some of those as we go along. Okay? But for the moment, we will summarize this part, saying solidification simulation is all about. First of all, simulation is all about an approximation to reality, but with the purpose that we can predict a particular problem or understand a problem which has already happened. Okay? And then several factors affect accuracy. We talked about mathematical model, the geometrical model, the way you divide it, okay, all the way to your heat transfer coefficients and your finally interpretation of the results. So that's where we introduce the concept of feed path, which will help us to interpret, but we'll go into feed path little more detail in another lesson where we'll give actual examples of interpretation of these feed paths. Okay? So we'll stop here with this lesson.